This video we'll talk about galvanic cells. Galvanic cells, which gives us some insight, or we can see how we're able to harness the electrons from redox reactions, right, for various applications. So before we talk about them, let's look at an example of a redox reaction between copper and silver. So if we have a piece of copper metal and we add it to a solution of silver ions, this is our reaction here, right? Copper solid plus silver. What we will see is that the copper will go into solution and the silver will precipitate out. Now, if we do this directly in a test tube, we'll actually see the silver metal precipitate on the surface of that copper metal strip, right? And then we'll see this solution, the color of the solution change as our copper 2 plus ions form in solution. Now, what if we so this is an example of direct electron transfer, right? If we do this reaction in a test tube, there's a direct transfer of electrons from the copper to the silver. Now, if we force these electrons to pass through an external wire, right, here's an example of this. So we have a copper wire. This test tube has a solution of silver nitrate. We submerge the copper wire into the solution of silver nitrate. We see the solution turn blue, right, indicating that copper 2 plus ions have formed as a result of this oxidation. And then we see reduction of silver by this gray solid that precipitates on the wire. So if we thought about how we would do this in a galvanic cell, so let's talk about what is a galvanic cell before we look at an example or look at that particular reaction in a galvanic cell. So with galvanic cells, you'll also hear voltaic cells. I just want you to know that they mean the same thing. I will consistently use the term galvanic cells. So this is a device where the two reactants, the one that's being oxidized and the one that's being reduced, are separated. They are not physically in contact, so that the electron transfer is indirect. We can actually like isolate or do something with those electrons. And so because we have the oxidized agent and the reducing agent in two separate half cells, they are like compartmentalized into what's called half cells. Half cells. So in one half cell, we have an anode, right, which is where oxidation happens. And then we have another cell that contains a cathode where reduction takes place. So the anode and cathodes are both electrodes, which essentially just allows for the flow of electrons, right? That's what an electrode is. So we have oxidation in one half cell that's producing or losing electrons, right? Producing electrons. Those electrons move through an external wire called the external circuit from the anode to the cathode, and these electrons can then be consumed in the reduction half cell. And so because these electrons are moving through this external wire or external circuit, they can be used as a source of electrical energy, right? Which can then be converted into other forms of energy to carry out some type of work. All right, some other things. which I've already said, right? The oxidation and reduction half reactions are happening at separate electrodes. They're happening at separate electrodes. The oxidation reaction occurs at the anode. And so we have anions that flow to the anode and electrons flow from the anode. So I know I'm throwing a lot of terms at you, but I just want to go through this and name the terms, and then we'll look at an example. The reduction reaction occurs at the cathode. So electrons, right, are flowing from the anode to the cathode. So that says from to, it really should just be to, right? Electrons flow. That's what that means. That's what that should say. I'm sorry. Electrons flow to the cathode. And let me just change this right here. They flow to the cathode. So they flow from the anode, oxidation, to the cathode where reduction takes place. These anions and cations, we're talking about charge neutralization, right? Balancing out the charge. And we'll talk more about that when we look at an example. But just remember that the anions are flowing to the anode, and we have cations that are flowing into the cathode. All right, so here's our galvanic cell for that same example we looked at between copper and silver. So we have each of these beakers, right, are considered our half cells where our half cell reactions take place. So here, this is our oxidation half cell. So we have a copper anode. This is the electrode that allows the electrons that are produced when copper solid is oxidized to copper 2 plus. Those electrons will flow through the electrode, right, through this external circuit to our cathode. Our cathode is silver in this case. So we have this solution of silver nitrate that's being, where our silver plus ions are being reduced to solid silver on this cathode once the electrons flow through. So here is our half cell reaction. So our half cell reactions are like when we write the oxidation and reduction half reactions for a redox reaction, right? So our anode half cell reaction is our oxidation step, right? Copper solid is going to copper 2 plus, producing 2 electrons. Those 2 electrons that are produced will flow to the cathode, and in our cathode, at our cathode, the half reaction here is reduction. So this is our reduction half reaction, where we have silver plus receiving or consuming 2 electrons to produce silver solid. So this is our oxidation half reaction. This is our reduction half reaction. So the external circuit, or you may see voltmeter here, this indicates the cell's potential, right? So it's a measure of the electron flow from the anode to the cathode. And the salt bridge, the purpose of the salt bridge is to make sure that our charges remain balanced. So the salt bridge is this porous device that consists of a salt solution, which is usually sodium nitrate. You may also see potassium nitrate there, right? So at our oxidation half reaction cell, right, In our oxidation half cell, we have this build up of positive charge, right? Because in our oxidation step, we're producing copper 2 plus. So to balance out that positive charge, the nitrate ions are going to flow into our oxidation half cell to balance out that charge. In the reduction half cell, we have a loss of positive charge, right? Because we're going from silver plus to silver neutral, right? As the electrons flow, we're losing positive charge. So that's why our sodium ions flow into the cathode to make up for that loss. And so the salt bridge's whole purpose is to make sure that we balance the charge between both half cells, right? It balances out the charge so that we can complete this circuit of electron flow, which can then, right, the electrons that's flowing through can then be used as electrical energy to carry out some function. Okay, so I've said this, but just I want to make sure that there's nothing that I haven't said. So remember, the salt bridge is a porous material. It contains a concentrated salt solution that's usually sodium nitrate or potassium nitrate. The anions are going to flow toward the anode, right, to neutralize the buildup of those positive charge ions, and the cations are going to flow toward the cathode to make up for that deficiency or loss of cations that are being consumed. So the salt bridge enables electrical neutrality, right, to be achieved so the circuit can be complete and the current can, we have a continuous current flow. All right, so that's our introduction to the galvanic cells.